Hello and welcome to the next webinar in a series being presented by the Electricity Sector Climate Information or ESCI project. For those who haven't been exposed to the project, the ESCI project is funded through the Department of Industry, Science, Energy and Resources and is undertaken by CSIRO and the Bureau of Meteorology in conjunction with the Australian Energy Market Operator, AEMO. My name is Rebecca Gregory and I'm the CSIRO project manager for this project. Before we get started, I just need to mention a few housekeeping items. As you can see, you've all been muted and have your videos turned off. This is to reduce feedback and distractions for the presenters. But please use the chat function on the Zoom toolbar to ask questions throughout the webinar, and these will be answered by the presenters during a Q&A session at the end of the presentation, and we'll address as many as possible. Today's webinar is entitled Scenario Analysis, Confidence and Uncertainty, and it's being presented by Kevin Hennessy from CSIRO and Ben Jones from the Australian Energy Market Operator. Kevin has been involved in climate change research for over 30 years. His expertise is in regional climate projections for Australia and the Asia Pacific region, and he's also an IPCC lead author. Ben is a forecasting specialist with extensive experience in electricity system forecasting, asset management and planning. He currently works to incorporate climate and resilience considerations in longer term planning processes. So now I'll hand you over to Kevin to start the presentation.
Thanks very much, Beth, and Beck, and welcome to everyone. Ben, if you wouldn't mind just putting up the first slide. Just by way of background, for those that don't know much about the ESCI project, it's running over about 2.5 years. Beck mentioned the different partners involved. It's actually quite a large project, $6 million, funded by the federal government. And the idea is to improve the quality and the availability of climate information for using in risk assessment for the electricity sector. So Ben, the first slide, thank you. Ben's just going to share his screen and then I'll get into...
I had it on the right slide, but I have not sharing my screen yet. It's the equivalent of speaking on mute. There you go.
Thanks, Ben. So the first part of this presentation is to just give you a little bit of background in scenario analysis. And the idea, of course, is to appropriately incorporate the potential effects of climate change into planning processes. So you need to understand how climate-related risks and opportunities may evolve and the potential business implications. So one way of doing that is through scenario analysis, and those scenarios must be plausible, distinctive, consistent, relevant and challenging. And this information comes from the Task Force for Climate Related Financial Disclosure, the TCFD. Next one, thanks Ben. So we did mention plausible scenarios are required, but they need to consider different levels of severity from best case through to worst case, designed with clear objectives, and including stress tests that really are targeted to the particular business risk profile. And we need to be very clear about the various assumptions and limitations, so they need to be well documented and justified. And of course, you know, in parallel, we're going through this with regard to COVID-19 exit scenarios. So do we do things like rebound, reboot, or reinvent ourselves? There are opportunities and risks in all of those different scenarios. Next one, thanks, Ben. Now, uncertainty can be quantifiable or unquantifiable. Quantifiable uncertainty can be expressed as a quantified range of possibilities supported by various lines of evidence, whereas unquantifiable uncertainty is due to knowledge limits or ignorance or inherent unpredictability, and that's certainly the case in some of the climate system. There's a really nice paper by McCollum earlier this year which looked at energy sector modelling and emphasised the point that personal views or cognitive biases can influence your thinking around what is possible. So we need to be very expansive and open-minded about the full depth of future possibilities. Next, thanks, Ben. With regard to future climates, there are three main sources of uncertainty. One is the future range of global emission scenarios of greenhouse gases and aerosols. Greenhouse gases have a warming effect, aerosols have a cooling effect. The second is the regional climate responses, and in particular the extreme weather and climate responses to each of those emission scenarios. And the third source of uncertainty is random climate variability at all timescales, from daily through to monthly, yearly, decadal, and beyond. So in the coming slides, I'll just touch upon each of these three sources of uncertainty. Next one, thanks, Ben. So firstly, emission scenario uncertainty and how that relates to global warming. This table is from the Intergovernmental Panel on Climate Change, the IPCC, which shows in the first column on the left, different emission scenarios. These are actually representative concentration pathways, or RCPs. 2.6 is a very low emission scenario, whereas 8.5 is a very high emission scenario. As we move across this table into the near term, the years 2031 to 2050, the mean global warming for each of those emission scenarios is shown. And you can see that there's not much difference in the mean global warmings for RCPs 2.6, 4.5, and 6, but RCP 8.5 is a bit higher. And the likely ranges of uncertainty, the range defined by the 9th to 95th percentile, is shown in that third column. So there are different estimates of global warming that come from different climate model simulations. There's not a single number. As we move to the end of the century, centered on the year 2090, we see the mean global warmings in the second last column range from about 1.6 degrees for RCP 2.6 up to 4.3 degrees for RCP 8.5. So it really does matter toward the end of the century which emission scenario you're following. Now, the Paris Agreement, which was signed in 2015, aims to limit global warming to less than 2 degrees by the end of the century. And RCP 2.6 is perhaps a best case scenario because it has a 2/3 chance of limiting global warming to less than 2 degrees. RCP 1.5 has about a 1/3 chance of reaching that target. And of course, RCP 8.5 is very much a stress test. Next, thanks, Ben. Another way of looking at that same information is to consider the time transition toward different levels of global warming for the different emission scenarios. So with RCP 2.6 as shown in this plot, we've got the global warming on the left-hand axis running from the year 1850 through to the year 2100. And these different lines are from a number of different climate models that simulate the climate system. The multi-model mean, I think this is an average of about 30 or 40 models, is shown in red. And you can see that increasing slowly over the 20th century and into the 21st century, but then flattening off after about the year 2030 or 2040. And this is because the slowing of the emissions is having an impact on the rate of global warming. So the multi-model mean, the MMM, is only 1.5 degrees around about the year 2039. Then if we now click on the next part of this slide, we can see what the equivalent transition of global warming looks like for RCP 4.5 and RCP 8.5. So now the warming rate is a bit faster for RCP 4.5 and even faster still for the very highest emission scenario. And the grey area at the end of each of these curves represents the uncertainty that you get from looking at different climate model simulations of the future. So not all climate models are the same. They all have strengths and weaknesses. If we had one perfect model, that's the one we would use, but that doesn't exist at this stage. So we need to look at multiple models and various different lines of evidence. Next one, thanks, Ben. So if we synthesize this as the IPCC has done, this is a very simplified plot that shows the transition from historical global warming through to future global warming. And it's just showing the very lowest emission scenario, RCP 2.6, and the very highest emission scenario, RCP 8.5. And you can see a very clear separation of those two global warming curves around about the year 2030 or 2040. So not much difference in those warming curves prior to 2030. And another way of thinking of this is that the RCP 2.6 warming by 2050, which is shown if you look at the green line, it's very similar to what you would get for RCP 8.5 in 2030, about 20 years earlier. So there are different ways in which you can interpret this based upon whether you're looking at the amount of global warming or the timing of that warming. Next one, thanks, Ben. So that's the uncertainty that you get from looking at different emission scenarios. What about the regional climate responses to those emission scenarios? So moving beyond global average warming to what it means for the Australian region. Well, firstly, we look at multiple lines of evidence, and this includes looking at observed trends in regional climate responses, understanding the physical processes that go behind those responses, looking at global climate model simulations, and there's about 40 of them around, but also looking at downscaling, and this gives us more detailed information, and particularly the potential for better simulation of extreme weather events. And there are both dynamical methods and statistical methods of downscaling. And on top of all of this, we use expert judgment to try and synthesize what this means. We select global climate models that perform well in evaluations. There's a lot of effort that goes into assessing that performance at a regional level for a number of different climate metrics, including temperature, rainfall, humidity, wind speed, and extreme events. As I said, we look at multiple climate models and multiple downscaling methods, not just one model or one method. We want to be able to quantify the uncertainty that comes from different models or methods. And we try to express this as firstly a central estimate of change and a range of uncertainty. So it might look like plus 10% for rainfall change, for example, with a range of uncertainty of 5 to 15%. Now, if multiple hazards are being considered, so for example, changes in temperature and rainfall, we need to use scenarios that are internally consistent and physically plausible. And that means not mixing up the results that you get from different climate models, because it might give you some implausible combinations. So if you have one climate model that gives you, say, a warming of 1.8 degrees and a scenario of 10% less rainfall, that is internally consistent and physically plausible. Similarly, a second model that gives you a warming of only 1.2 degrees and a 5% increase in rainfall is internally consistent for that model. But if we were to mix the warming from model 1 and the rainfall change from model 2, it gives you a combination that might be implausible. So we need to be very careful about how we mix the ranges of uncertainty for different climate variables. Next one, thanks, Ben. I'd like to just give you an example of what climate change looks like for different individual climate models. This is a Norwegian climate model, and we're looking at projected changes in temperature and annual average rainfall for the year 2050 for the very high emission scenario, RCP 8.5. On the left, we have the map of temperature change, and you can see on the vertical scale there, we're looking at patches of light yellow, which are between 1 and 1.5 degrees warmer, and patches of darker yellow, which are between 1.5 and 2 degrees warmer. And if we look at the equivalent change in rainfall, over most of Australia, the changes are fairly neutral between -2.5 and +2.5 degrees. Some patches in white, which are between +2.5 and +7.5 degrees. And over in the west, and in parts of Western Tasmania, we're getting even stronger decreases in rainfall between 2.5 and 7.5%. So that's the result that you get from one climate model, which is relatively weak in terms of its response to the emission scenario. If we go to the next slide, Ben, this is a model which has a very strong response to a high emission scenario. So now the temperature changes on the left-hand side there are well above 2.5 to 3 degrees over most of Australia. And the rainfall changes are incredibly dry. So we're looking at changes in parts of central Australia exceeding 27.5%, and over much of the rest of the country, certainly around 7 to 17%. So that's a very, very hot and dry model compared to the previous model, which would have been warmer with little change in rainfall. So we need to consider this variability when we're assessing the uncertainty at the regional scale. Next one, thanks, Ben. The third source of uncertainty is random climate variability from daily through to decadal timescales, and this strongly affects extreme weather events. The main modes of variability include the El Niño Southern Oscillation, called ENSO. This is centered in the Eastern Tropical Pacific, but has an effect on all parts of the world. The Indian Ocean Dipole, which, no surprise, is centered in the Indian Ocean. That's called the IOD, and that has an influence on parts of Australia. And finally, the Southern Annular Mode, which is down south of Australia. You can see it on the diagram to the right there, centered in the Southern Ocean. So each of these things has a strong influence on our weather and climate. Next one, thanks, Ben. So firstly, ENSO. During El Niño conditions, rainfall's often below average. We have fewer tropical cyclones, and heat waves are more likely. And you know, the conditions that were very obvious in the early 1980s and parts of the 1990s and through to the mid 2000s, a lot of very strong El Niño conditions there with heat waves and fires and so on. The opposite happens during La Niña events, and right now there's about a 70% chance that we're moving into a La Niña. So in that case, we expect slightly cooler conditions, a bit more rainfall, and more tropical cyclones. El Niños occur every 3 to 5 years and can last for 6 months to about 2 years. And the last El Niño was in 2015-16. La Niñas occur every 3 to 7 years. Interestingly, half of all of these La Niña events have lasted 2 to 3 years, and 40% of all La Niña events are followed by a La Niña. Next, thanks, Ben. With regard to the Indian Ocean Dipole, when it's in its positive phase, that can lead to drier and warmer conditions with increased fire risk in winter and spring over central and southern Australia, whereas the negative phase has the opposite effect. And the Southern Annular Mode, when it's in its positive phase, gives more rainfall to eastern Australia with more east coast lows, and we've seen a few of them recently. That can lead to flooding and storm surges and coastal erosion. It also produces less rainfall in the south, and the opposite effect when you have a negative phase of the Southern Annular Mode. Next one, thanks, Ben. So when looking at the climate model simulations of the future under increasing greenhouse gases, we find that there's an increase in the number of strong El Niño events and strong La Niña events. So that means more floods and more droughts, unfortunately. There's also a tendency for more positive Indian Ocean Dipole events, and that means drier and hotter conditions in winter and spring, affecting parts of southeastern Australia. And more positive Southern Annular Mode events, which means more rainfall in the east, but less in the south. So all of these important modes of variability need to be captured in our climate projections at the regional scale. Next one, thanks, Ben. So we've looked at those three sources of uncertainty. An important part of the story now is to assess our confidence in regional climate projections and the likelihood range that can be associated with those projections. And the IPCC provides guidance on how to do this. The first thing, if we look at the top left box, is to evaluate the evidence available and the agreement amongst those lines of evidence, and then consider what can be said. If we follow the arrow immediately to the right, this is if there is insufficient evidence and insufficient agreement to actually evaluate confidence. It might give you a very, very low confidence rating. In that case, you would just present a summary and perhaps a qualitative summary of what the projections might be for the future, or you might just say, we don't know. And for example, with regard to hail in future, there is limited evidence and certainly not much agreement on where that's going to go in future. So at this stage, it's highly uncertain. However, if we have sufficient evidence and sufficient agreement to evaluate confidence, we follow the arrow down toward the middle of this slide and we can evaluate confidence. And if the evidence doesn't allow a probabilistic assessment of uncertainty, then we just present a confidence rating. And that can be low, medium, high, or very high if there's a lot of agreement and a lot of evidence. If the evidence does allow a probabilistic quantification of uncertainty, then we can express a range of changes, a likelihood or a probability range. And sometimes that might be the 5th to the 95th percentile range or the 10th to the 90th percentile range. But we can quantify both the range of uncertainty and associate that with a confidence rating. That's where we would ideally like to be. Not always possible, but that's what we try to do. Next, thanks, Ben. So the confidence ratings that are recommended by the IPCC are as follows. So if we start down in the bottom left-hand corner, where we have low agreement amongst the different lines of evidence and limited evidence, so you might, for example, have one peer-reviewed journal paper that indicates a particular change, that would give us low confidence in the projected change if we were to make a summary assessment. On the other hand, if we move to the top right-hand corner, where we have robust lines of evidence, all with very high agreement, then we have high or indeed very high confidence in the projection. So there's quite a process involved amongst experts to assess the amount of evidence and the degree of agreement. And as I said before, we look not only at climate models, but we look at our understanding of physical processes, we look at observed trends, and we look at downscaling. Next, thanks, Ben. So with regard to likelihood, it does depend on the nature of the probabilistic information that's available, but we try to present either a complete probability distribution, and it's great if you can do that, or a percentile range, as I indicated, perhaps the 10th to the 90th percentile. You don't want to just give a central estimate because it will not give sufficient evidence to the full range of uncertainty, and we really do want to sample the full range of uncertainty. Now, the IPCC encourages scientists to provide information where possible on the tails of the distributions, because it's these low probability, high impact events that have the biggest risks. So we do need to consider things like the 1 in 10 year extreme rainfall event or the 1 in 10 year extreme fire event. Next one, thanks, Ben. So just trying to pull all of this together in a very simple synthesis. There are three main sources of uncertainty. So firstly, there's the uncertainty about the way greenhouse gases and aerosols may change in future. Secondly, the regional response to each of those emission scenarios. And thirdly, the internal climate variability at all timescales. And the graphic on the right-hand side here is just showing you a representation of what that might look like, for example, for temperature in winter. And this is just indicating that in the short term, let's say up to 2040, most of the uncertainty is going to be due to internal variability in the climate system. That's going to dominate over what we call the forced climate change signal. But as we move further into the 21st century and say we're out to the year 2060, then the scenario uncertainty, which is the difference between high emissions and low emissions, is really going to play a much larger role in contributing to the full range of uncertainty. And the response uncertainty, which is the second source that comes from looking at different climate models, is fairly constant across the whole century. So short-term internal variability dominates, longer-term the emission scenario uncertainty tends to dominate. Next one, thanks, Ben. And this is where I hand over to Ben, so over to you.
Thanks, Kevin. Yeah, I'm going to take over now, and I think extending beyond what Kevin's described as the source of uncertainty in the climate projections, I'm now going to have a go at some of the things that we've discovered through the project and some of the things we've discovered in AEMO as to the ways that we can blend the way that climate scientists model uncertainty with the way that the electricity sector models uncertainty. I think there's several things that can be used to describe the electricity sector. It's highly quantitative and in many cases highly probabilistic, and there's many things about the electricity sector that mean it's highly uncertain. So the idea of working with uncertainty for the electricity sector is not so foreign. We're going to start here with the proposed ESCI risk framework, which is putting a framework around how the sector can approach assessing climate risks, working through a standard risk assessment process to be able to identify what are the likely impacts from climate change on electricity sector decision making, and also what does the range of uncertainty mean, and how can the sector include that range of uncertainty in the decision making process. So it starts first with a pre-planning step, which is about identifying the vulnerability and understanding the decision in question. Now, the project's identified several target decision-making processes, and these are processes related to how resilient the power system is and how we operate the power system into the future. Decisions relating to how reliable the power system is, whether that be distribution network reliability, transmission network reliability, or whole power system reliability, and also investment risks. How could a new proponent use climate information to better make an investment decision, whether that be a generation investment or a transmission or distribution network investment? Step 2 in the process is about using the tailored climate information to scan for and quantify physical risks. And this includes information across all of those 3 sources of uncertainty that Kevin identified. But there's several sources of information that's being provided to assist with that. And then step 3 in the risk assessment framework is around about using that information to identify whether or not the risks that are emerging are material against objectives, whether the uncertainty is material against objectives, and to generate adaptation pathways and justify investments and system changes needed. So the stepping out those 3 data sources a little bit more, we've got the target long-term processes at the top, and there's several use cases within there that I'm going to talk a little bit more about later. So some of the key use cases that the project's really targeting relates to forecasting and modelling of power system performance, particularly forecasting that might support transmission planning processes, or forecasting that might support generation modelling and new market entrant modelling processes, and also the type of system modelling which would support distribution, transmission and system reliability assessments. All of those forecasting processes have to accommodate substantial uncertainty in the future, the way that the customers might consume demand, of the way that the market might evolve, etc. Against some of the key hazards that have been identified for the project, things like temperature, wind, bushfire and precipitation, there's 3 main sets of climate information. So we're providing trends in key climate variables that affect supply and demand that can plug into many of these processes that allow us to understand several different simulations across several of those different climate projections, how all of the variables are changing in an internally consistent way. Also looking at high impact weather simulations of compound extreme weather events to really stress test power system and power system components, and regional thresholds for key climate variables, which are really looking at what is the mean and the uncertainty around extreme events like extreme single variable impact, so things like extreme temperature, extreme wind gust and bushfire weather. And the project will be producing numerous outputs like data products, guidance, training and case studies. So just like Kevin was saying in the climate projections, the uncertainty changes over time. In the near term, the uncertainty in the climate really relates to more weather and annual patterns in weather. But in the long term, the uncertainty is really driven by policy settings and international action to reduce greenhouse gas emissions. If we look to the energy sector, it's almost an identical problem, that the uncertainty in the short term for energy forecasting is related to things like consumer behaviour. What will consumers do tomorrow? How will they respond to the weather that's happening now, next week, next month. And industrial activity is also a key part of uncertainty in energy forecasting in the short term. As we move out to the medium term, the uncertainty in energy projections also changes. It also gets wider as more things become variable. So in the medium term, in that kind of 1 to 10 year space, you see the power system might change with investments. There's likely to be changes in the way consumers own and use appliances, and this includes things like distributed energy resources like rooftop PV, electric vehicles, those types of things. And there's also quite a lot of uncertainty in the economic growth and population trends. These all need to be considered in energy models. Whereas when we get to the really long term, which for AEMO is kind of our 10 to 30 year space, we have to consider an even broader set of uncertainties because there's many structural things that could change in the energy sector between now and 30 years away. So we need to be looking at different scenarios of policy and investment changes. What are the possible pathways for economic and demographic development, and also what are the technology changes which might influence the price of certain different technologies or the way that consumers implement those technologies. There's actually quite a lot of overlap between the way climate projections are assessing uncertainty and the way that the energy sector assesses uncertainty. If we start thinking about the long-term forecasting, whether this be a transmission planner identifying the needs for their transmission network, or AEMO doing long-term forecasting of how the power system is likely to evolve, there's a standard industry practice to represent that uncertainty in two parts. So the sector does so firstly by identifying a selection of scenarios which are pinned to structural drivers. Now these structural drivers are typically assigned a stake in the ground and say, if this happens, what would be the outcome? And that scenario is not subject to any further uncertainty. So it's common for things like structural drivers for the sector to develop a set of scenarios that are related to things like a particular population trajectory, a particular economic growth trajectory, price, technology, generation, production, and it might be worth considering whether greenhouse gas emissions policies needs to be in there as well. Within each one of those structural scenarios, it's also common to apply random drivers. So for example, while we might be able to develop a scenario that tells us, well, this is consistent with a high emissions scenario, or this is consistent with a high economic growth scenario, there's still substantial uncertainty that sits within that related to some of the things which can't have that stake in the ground that say it won't, we can't say that. And some of those things are how consumers respond to weather. What will be the weather in a given year? And how will consumers respond to that? How will consumers respond to non-weather driven patterns? So things like diurnal patterns and weekdays, and things that affect the way that people live their lives. Weather driven generation output obviously can't be known because for every year we don't know what the weather will be. And then there's other factors that relate to how the power system performs, transmission failure rates and how available generators are, and generator failure rates and their available capacity. So it's kind of common for there to be a set of scenario that says economic growth will be this, but within that particular scenario, there's still a probability distribution representing the unknowns, that weather is unknown, that consumer behaviour is unknown, that renewable generation output is unknown, and we tend to represent those random drivers as probability distributions. An example of this, I've taken this from some of AEMO's publications, where we've got two variables here that demonstrate these in application. The first being are three different scenarios that show what were AEMO's assumed residential connection growth rates. So you can see here, we've got three scenarios, a slow, neutral and fast change, and there's been three assumed residential connection growth rate, 1.6% growth, 1.8% growth and 2% growth. So that it's indicative of a scenario that's constructed using deterministic forecasts of these structural drivers. But within each one of these scenarios, they also have those random drivers that show what's the probability distribution of possible outcomes within that structural scenario. And this graph here demonstrates where the model has been used a Monte Carlo approach to identify what's the possible range of outcomes, given that weather is uncertain, given that consumer behaviour is uncertain, and given that variable renewable output is uncertain. What is the simulated temperature at time of the annual maximum demand? And what this particular simulation shows is that for South Australia in this particular forecast, the annual maximum demand might fall at a temperature anywhere between 35 and 47 degrees. Further summarising some of those forecast components, you could see that for any one of the inputs that flow into forecast models, they might be deterministic or probabilistic, and then the model outputs might also be deterministic or probabilistic. So this is some of the way that AEMO is categorising this, that we have some deterministic or those structural components that define the scenario, and these include things like economic growth, energy efficiency, PV and battery uptake, new generator connections, and AEMO also now includes the concentrations of atmospheric greenhouse gas as a deterministic input to some of these forecasts. Whereas weather and the related time series impacts on consumer behaviour, for example, remains a probabilistic element. So we're already breaking that uncertainty, those three sources of uncertainty, and the way that AEMO's approached the problem is to say some of this we will say is deterministic and some we will leave in the probabilistic bucket. I'm now just going to go through a couple of examples. I'll start with some examples where of the way AEMO's approached this, say in the integrated system plan modelling, and then I'll also show a couple of examples as we deployed them in some of the ESCI case studies where we're prototyping the risk framework to solve industry problems. This first example is from AEMO's integrated system plan. AEMO's integrated system plan is our view of what is the lowest cost potential development pathways for Australia's energy systems under a variety of scenarios. And it's integrated because it's really looking across transmission investments, generation investments, and gas investments. And these 5 scenarios lay out 5 different pathways that the power system could take or society could take that would then deliver a lowest cost energy system in response to that. So while all of those inputs that I previously described are embedded in these scenarios, we've plotted them here on 2 different dimensions because these 2 dimensions are some of the most dominant in the evolution of the power system. So we've got a slow change scenario, which is very low amounts of distributed energy uptake, low amounts of energy demand, low amounts of renewable generation into the power system. And therefore it's still a very centralized power system and still a very carbonized power system, all the way up to the highest end of the spectrum. We're looking at very rapid amounts of all of these technology being deployed, high amounts of economic growth driving economic demand, but also a very rapid decarbonisation of the power system and a very rapid decentralisation of the power system. Within each one of those scenarios, we've now got this description that shows what was included in those scenarios. So things like, was there an emissions budget built into them? And what are some of the policies that sit beyond them? So the topic of this presentation today isn't the ISP, but some of the scenarios were set using harder carbon budgets and some with more policy-driven outcomes. And we're able to model the emissions outcomes of the national electricity market under a variety of these scenarios. Where it really becomes relevant for this project, though, is when we start turning away from the scenarios constraining the emissions within the scenario to the scenarios resulting in the physical symptoms of climate change on the power system. So within each one of these scenarios, we've constrained the emissions output to a representative concentration pathway. So it's a loose relationship, but there's a relationship established here that is saying that this scenario is associated with the lower emissions pathway globally, and this scenario is associated with the high emissions pathway globally, which can then be associated with a temperature impact and a reduction in precipitation which flows through to a hydro impact. This is very much about dealing with that long-term scenario uncertainty relating to the greenhouse gas concentrations in the atmosphere. Of course, within each one of these scenarios, there's then that probabilistic response to the weather, the extreme events, and the regional uncertainty that still needs to be explored. I've just brought back these couple of slides again because it's worth noting that in many of the it all comes down to how much you should consider different uncertainties comes down to what the problem is you're trying to solve. What we've found is that many of the problems in the electricity sector space are really looking at this next 20 years, at this next 40 years. And as Kevin indicated, if we look to the next 20 years, we see that the largest source of uncertainty is probably not the emissions pathways. A lot of them have a lot of overlap, being that a lot of the emissions are already baked in, the pathway is already baked in, and therefore we'll continue to get that warming that's associated with historic emissions. It's only when you start going out post 2050 that you really start to get that variation. So it's important to understand that, and this graph shows that as well, that if we're really looking in that 2020 to 2040 space, the largest source of uncertainty really comes from internal uncertainty, i.e. weather, or response uncertainty. How will each region respond to climate change or to the increasing concentrations of greenhouse gases? It's only when it becomes much later in the century that the scenario uncertainty becomes more useful. So depending on the problem you've got to solve, it may simplify the uncertainty that needs to be modelled. Here's another example where we've solved this problem in the project. These graphs show how the 1 in 10 year temperature, a POE 10 temperature, a temperature that should be exceeded no more than once every 10 years, how that's likely to change under RCP 8.5. Now, in this case, we've pinned it to 8.5. We've said it will be associated with a higher emissions pathway. And we're using this to try and understand what is the response uncertainty within there. If you were interested in a particular region, say somewhere about Mildura, you might be able to look between the various climate models in question to understand how is a POE 10 temperature changing. Say if you were using this for rating an asset, you had a transmission line that was running through Victoria, you might want to understand how are increasing temperatures going to decrease my output on that transmission line. You might be able to look to this and say it's going to be somewhere between 46, 48, 46, 48. It might give you an appreciation of the uncertainty that might in the POE 10 temperature, which you could use in decision making to understand, is that uncertainty material, is the change material, and if so, how can we incorporate that in decision making processes? This is another example where we've used this in our VRE, our Variable Renewable Energy case study, where we're looking at how the effects of increasing heat are changing generator output under peak periods being those 5 hottest days of the year. And what you can see here is we're not talking about individual models. What's been done to represent this uncertainty? Well, I should say again, once again, this one's tied to RCP 8.5. We're saying emissions will be high, but as opposed to collecting individual climate models, this one's been now represented as a probability distribution to say, look, maybe we don't need to know the individual models, but we want to understand the uncertainty that's coming from those individual models. So these show us the individual models have been processed to a power conversion model in a way that preserves their internal consistency, and then we've just assessed the uncertainty that's arising from those outcomes. So what this is showing is that for several sites around the country, we might see a slight decrease in the median power factor or median amount of output from solar farms in several locations during peak days, but there is substantial uncertainty around that, driven by weather and the regional response. Similar again, when we look to wind farms on peak demand periods, we can see there is a decreasing trend in output associated with wind farms during peak demand conditions, but there is also substantial uncertainty year to year, driven by the weather, or the uncertainty attributable to weather, and the response uncertainty within the scenarios. That might just be regional response or model response. And final example I'm showing again, which is in a very similar vein. Once again, we've tied the scenario to the RCP 8.5 and said emissions will be high because we want to understand what the impacts are going to be, and then we're assessing what the weather and regional response is within those models, which is allowing us to see things like, for forest fire danger index, which is a proxy for how bad fire weather is going to be, or how bad fire weather is, how can we express that uncertainty? So what this is showing is that for several thresholds, a low to extreme or catastrophic bushfire thresholds, how many days a year would we expect to be over that threshold? For Adelaide, and what this is showing is that we've got a distribution of possible outcomes now, and as the climate projections change, including both weather and the regional response, we're seeing a much wider distribution of possible outcomes in the future. And when we look to, say, this one here, which shows a much more extreme bushfire threshold, we might only expect to see around about 0.5, on average 0.5 of those days per year in the current climate. But as the climate evolves and the weather uncertainty grows and the response uncertainty grows, we might see that anywhere between 0 and 2.5 days per year over that threshold on average. These graphs are displaying the same information, but it's been displayed here as that full probability distribution of the possible outcomes, with a mean going through the middle of that to represent what the mean of the climate models show. So I think the importance of understanding the uncertainty is that it's good to know that the mean is changing, but if we were to look at some of the extremes and the changes in the extremes of some of the other climate models, would they have a material impact on the decisions we need to make, and how can we best represent that uncertainty in electricity sector decision making? I'll finish up there and very happy to take some questions.
Thanks. There is a few questions for both you and Kevin in the chat. So the first one, have you considered any synergy effects or interaction between the structural components on the forecast response?
Sorry, was that to me? Sorry, Beck.
For you or Kevin.
Okay. Sorry, Anna, can you ask it again?
Have you considered any synergy effect or interaction between the structural components on the forecast response?
Yes. So in the process AEMO goes through to identify those scenario characteristics, there are absolutely synergies between the two. So for example, economic growth is often thought of as one of the leaders, where you would expect to see if people are wealthier and have more disposable income, you might see that associated with a larger amount of renewable energy uptake or distributed energy resources like rooftop PV. So some of them certainly have relationships between them that need to be considered. They can't be fully independent. And similarly, the impact between how quickly the power system decarbonises and the resultant impacts on the power system from climate change also have a synergy.
Thank you. The next question says, with the climate already changing, how will these risk assessment processes link to current decision processes, such as the 5-year planning and capital cycles, which are relevant to building resilience?
I think that's where this project comes in, is that I think we've identified throughout the project that many of the industry decision-making processes are doing a really good job of capturing weather, but may not be keeping up with the changes in climate. So I think that's where this project really comes in, to work with the likes of the transmission planners who are developing those 5-year paths, and working with AEMO and also the distribution planners to try and understand how the decisions need to be updated to better capture investments which are fit for purpose in a future climate.
The next question is, won't chronic trend changes lead to a deterministic impact on transmission efficiency?
Yes, and I think that's somewhat covered in that the way that AEMO's doing it. I cannot say that everything I put here isn't saying this is what the whole industry should follow. We're more just, these are some ideas of the way that AEMO's approached the problem and the way that the project's identified some issues. It's something that we very much hope to do in some of the next version of the modelling within AEMO, is that we would then tie the ratings of the transmission elements to the deterministic scenario, so that if we're forecasting, or we're saying that the scenario is associated with a 1.5 degree temperature rise, that we should be incorporating weather which is associated with a 1.5 temperature, 1.5 degree temperature increase, which would then drive transmission ratings in line with that weather. So I think there's an indirect step here, and I think it's the indirect step from a future climate, which is deterministic, which results in future weather, which is probabilistic, which will result in impacts on power system outcomes.
There's a question which Kevin has partially answered. The question was, how would that fractional uncertainty graph look for another climate variable, say rainfall instead of temperature?
Yes, so my response to that was that, that there's actually a sample graph for rainfall in a technical report from a few years ago, and that shows that the uncertainty due to the regional response for rainfall is actually larger than it would be for temperature. So the climate models tend to have more agreement on the projected temperature changes than the projected rainfall changes. And you can imagine, for example, in Northern Australia, some of the models are telling us it's going to get wetter, some of the models are telling us it's going to get drier. So there's much more uncertainty with regard to rainfall at the regional scale.
Thanks. A couple more to go. The scale of data needs to be at a span level, approximately 400 metres, to provide meaningful analysis of pain points on the network. This can then consider other risk factors, e.g. span length, terrain and load. The examples provided have been at a national level, which isn't the best scale from my perspective.
Don't know if you want to answer that one, Ben. I had a crack at it just in the chat and just suggested that while the regional climate scenarios are relatively coarse resolution, so there might be information 100 kilometres apart, not 400 metres apart, those broad scale changes can be applied to the historical information to then provide future information that is still at the fine scale. So it all depends on having the historical information available and being able to sensibly apply broad scale changes to those baseline data. But Ben, what do you think?
I was very much agree. I think some of the biggest gaps we've identified in this project relate to gaps where the history isn't available. We don't even have that type of measurement of some of the variables. So without that historic evidence base, it's hard to project that forward. Certainly the global models and the regional models tell us a lot about how these things are likely to change. So if you've got a good historic data set, it would probably be quite sensible to manipulate that historical data set to make it fit for purpose in a future climate.
Okay, and is there any consideration of urban heat islands on local ambient temperature?
This is a really good point, and I'll let Ben answer just after I make an initial comment. We did something similar for the gas industry probably about 10 years ago. They were interested in both the effect of climate change and of future growth in urban heat islands due to population growth and changes in building materials. And the urban heat island effect had, I guess, an order of magnitude less effect than climate change, but it was still important to consider. So Ben, I think that would be one of your structural drivers related to population growth if we wanted to include it.
Yeah, so I think it's worth pointing out that most people in the electricity sector are interested in power system outcomes. So I think it'd be how is the weather and how is a change in the heat island effect affecting power system outcomes. It's probably not on the top of the list, because I think a lot of the weather stations we tend to use to correlate with power system outcomes are already quite urban and already quite affected. But I also know that the CSIRO model for downscaling has already put a lot of effort into heat island effects as well.
That looks like the end of the questions for now. So that brings us to the end of today's webinar. I'd like to thank Kevin and Ben for presenting such an informative webinar, and also to everyone who's attended for your time and your great questions. A recording of today's webinar will be made available on the ESCI page of the Climate Change in Australia website. If you have any more questions about today's webinar or the ESCI project, please don't hesitate to contact us. My email address is in the webinar confirmation email. Make sure you look out for the next ESCI webinar, details of which will be distributed shortly. Thanks again for attending, and we look forward to seeing you at the next ESCI project webinar. Thank you.
Thanks, Beck.
Thanks, Beck. Bye, everyone.